would like to, good afternoon, everybody. So I will talk about the satellite data and our global multi-annual MUSICA IASI H2O and delD pair product, and also on the new perspectives that will come up in the coming years concerning satellite observations with European satellite sensors. So, okay, first of all, there's a long list of people that contributed to this slides or to this presentation I show. I marked by bold these people that are directly involved in the satellite data. All the other people helped in interpreting the data and doing science with it or contributed this other kind of data. So first, I will present a bit the MUSICA IASI retrieval and the part of the H2O delD pair data set is part of a bigger effort of retrievals, and then also show the satellite pair data, the water isotope log pair data over West Africa, and briefly show what kind of science we can do with this there. And then also discuss a bit the potential of this isotope log data in the context of atmospheric analysis. Then also the two perspectives I would like to briefly discuss with you is that we can actually provide this data for rather long periods, that is for 15 years right now, and there's a really a perspective to do it even longer. This I would like to discuss it briefly with you. And then also there's the possibility to retrieve profiles of tropospheric isotope logs. And finally, a summary and outlook. So this is just a brief overview of the whole MUSICA IASI retrieval. So it's not only water isotope logs, it's also greenhouse gases like N2O, methane, and also HNO3, which is important for stratospheric chemistry. And you see here the highest spectral resolution of the satellite. Yes?
Yes, we still see your first slide, so I think you need to stop sharing the screen and then share your entire desktop, so that we see the slide advancing.
Share, so I share screen. Okay, maybe I have here another option.
Yeah, perfect.
Is this now better?
Yes.
Okay, so so sorry, there was another option to share. Okay, so now. Okay, so this is just an overview of the MUSICA IASI processing. And as I mentioned, this is not only water isotopes, we have other products. You see here the typical spectra measured by this thermal nadir sensor. So it's an instrument that's looking downward from space, and it's measuring thermal radiation from the surface and how this radiation then goes through the atmosphere and is affected by the atmospheric trace gases. And so we have information about water vapor. You see here on the right, the averaging kernel, which informs about the sensitivity with respect to the different trace gases on the diagonal of this block matrices. You see here first water vapor, then delD. How is the sensitivity? You see here water vapor. We have a lot of detailed sensitivity concerning the profile. For delD, we have maybe two independent altitude regions that we can resolve. Then also for N2O and methane, yes, we have also maybe two independent pieces that we can resolve concerning the vertical distribution in the atmosphere. But okay, now coming to another look on the data. You see here the small film where you see here the two satellites that have been in orbit since 2014. In the meanwhile, there are 3 satellites, but already with 2 satellites, we have a very good global coverage. This is just a film for 1 day of observations. You see there's observations during daytime, during nighttime, and you can cover really the whole globe within twice within 24 hours. So 1 overpass during day, another overpass during night. And okay, now coming to the water isotope log data, this is really calibrated data because we also had in this MUSICA project an aircraft campaign where we had really very resolved vertical profiles for the water isotope logs from sea surface up to 7 kilometers that we then on which we then applied the smoothing function of the satellite, and then we could really validate our satellite product, and we see a good agreement with the in situ references. So what we actually are interested in is the isotopologue, the pair product. This is the pair of water vapor and the isotopologue ratio between H2O and H2O. This is what we're interested in. And this measuring this with remote sensing technique is not that easy actually, because it's not the same to do an individual retrieval of H2O and HDO. This would give us a lot of noise in the ratio data, because the problem is that we have different sensitivity for the two water molecules. That is, the heavy isotopologue has different sensitivity than the standard isotopologue, and this causes really problems. So what we have to do, we have to really focus on the retrieval of a ratio directly. That is, we have to constrain the ratio in our retrieval process, and this is shown here in the center panel of this averaging kernels. But this is still not actually what we want to have, because we want to have H2O delta D pairs. That is, we want to have vertical resolution that is the same for delta D as for water vapor. And therefore, we have to do a post-processing where we really achieve that we have the H2O parameter we retrieve with the same vertical characteristic or sensitivity as the delta D parameter. And only then we can really look on the H2O delta D pair distribution that we see in our remote sensing data. So this is really an important point I would like to make here. And this is then an example of what we get. We have here on the left a global map of observations in August 2014, and I just mark here 4 different regions where we have a different H2O delta D distribution. Of course, in Alaska, the signal is coming because the evaporation takes place over low latitudinal ocean or low latitudinal ocean. Then via transport through higher latitudes, it gets more and more depleted by rainout. So you are here with this H2O delta D distribution along a Rayleigh line or on a Rayleigh line, and the other signatures here in the subtropics, they might be explained by mixing between dry and air masses. But looking here on the right, I would also show you a bit the typical vertical information that we have in this data. So for a tropical observation, you see here that we have even some profiling capability, so that we can distinguish between isotopologues that are observed between, let's say, 6 and 1 kilometer above surface, and also a layer higher up between 3 and, let's say, 8 kilometer above surface. And at higher latitudes, we don't have this profiling capability. And this is also shown here on these global maps for morning and evening overpass for February and August. You see here, red means here that we have profiling capability. Blue means that we have no profiling capability. And you see that here, that you here have for lower latitudes, you typically have a profiling capability. Then also an overview on the uncertainties of this data product. The uncertainty for H2O shown on the left, also for February and August for typical day, and for evening and for morning overpasses. Typically it's 10% for water vapor, and for delta D, the uncertainty is typically between 10 and 20 per mil. But you have larger errors at very dry atmospheric conditions here seen in the subtropics. You have errors that can reach 35 per mil. Okay, and for more details on this data set, there recently appeared a paper by a former PhD student here in Earth System Science data, where you have really detailed information on this data set and how it can be obtained. Okay, so now I would like to briefly show you some usage of the data. First of all, for studies over West Africa, and this first has nothing to do with our observations. It's more or less precipitation data that here simulated for West Africa with different model setups for different seasons, for November, July, May, and February, and with different degrees of sophistication of the model. And on the right here, you see observations, which are from the Global Precipitation Monitoring data set from NASA, which is the iMERGE data set. And so this is the truth, actually, what you have here on the right, and this is on the left. It's the model calculations, and you see you really have to increase significantly the degree of sophistication in your model to get more or less a good agreement with what is actually observed. This means really, and the idea is, can we use the isotope logs to better or also to evaluate, how good do this are these precipitation events, or how good is the cytological cycle in the atmosphere modeled by the different model setups. And to do so, what we did actually, we focused really on these rain processes, and we again used this iMerge data, and we set up a kind of mask. So we defined events that are not affected by rain, and the condition was that at least 24 hours or at least 48 hours before the observation of the satellite, there was no rain during the last 48 hours before the observation. And then we classified another group of observations that was observations that are affected by rain or by precipitation. And this we defined as that there was 24 hours before the observation, there was a rain event. So we used the iMerge data for this classification. And then we look here, what you see here on the right side, then we look on our IASI data, what we see. And if there was a rain event, this is the red contour lines here in this H2O delta D distribution, we see here a clear signal of super Rayleigh processes. And so this can be clearly observed here in the data, but if there was no rain, we see more or less a behavior which is typical for mixing processes. So it looks that we can really well identify with the isotope locus observation, we can really well identify moisture in the atmosphere that has been affected by convective processes. And this here is also actually the same, but here on a climatological scale. So we do this here for the whole seasonal cycle, not only for individual rain events, just to look here how this H2O delta D distribution is with respect to the different seasonal seasons. And you see here also in the rain season in August, there's really a clear super Rayleigh signal in the data. Okay, so then another thing I would like to discuss briefly with you is to use the isotope log data for assimilation purposes. And the advantages of the satellite data, we have them really globally available, daily available, and with a good, very high horizontal resolution. So it's actually a perfect data set for doing data assimilation. And this is done here in collaboration with the Japanese group, where we have a German-Japanese project at the moment. And we use a local ensemble transform Kalman filter for this assimilation. And this assimilation actually works that we have a large ensemble of model runs. And in this models, in these ensembles, we identify covariances between the isotope logs and different atmospheric parameters. And always, if there is a covariance between the isotope logs and any atmospheric parameter, of course, there is information in the isotope log that can be used to improve the knowledge about these atmospheric parameters. And this is how this assimilation system works. And actually, what we did, here, what we did actually, we made different assimilation experiments. First, a reference run where we assimilated typical standard data that are used by assimilation systems of weather services, which is radiosonde data or surface data of pressure, temperature, humidity, and wind. And then, in addition to this data, we made we assimilated humidity from IASI, delta D from IASI, and humidity and delta D from IASI. And look how the knowledge or how the analyzed product improves with this additional assimilation. And this is shown here. So the measure for deciding if there is improvement with the additional assimilation of the isotope logs is this skill value. So the skill value is just the reduce in the root mean square error, which is defined here as the difference of the mean of the ensemble with the actual truths that we know, because we simulated with a model data. So it's a real completely theoretical study. It's an observation system simulation experiment. And so actually, if we have positive skill values here, we can say that the additional assimilation of the IASI data as humidity or isotope logs improves our knowledge of the atmospheric state. And this is shown here on this plot. You see here the reference is always the control run. That is always the skill with respect to the assimilation of the standard methodological data. And you see here assimilation of IASI delta-D improves our knowledge, but also assimilation of humidity from IASI improves our knowledge. But the best, the smallest uncertainty in our knowledge of the atmospheric state is if we assimilate both humidity and delta-D. So there is really useful information in this H2O delta-D data. Okay, so then coming to the perspectives, the first perspective is that that IASI is really an incredible instrument. I mean, it's in orbit since 2007, at the moment on 3 different satellites, and it is already scheduled and approved for being in operation until the 2040s, the successor instruments of IASI. And this really, at the moment, we already retrieved 7 years of data, but we could actually go back in time and start with reprocessing from 2007 to 2014 also. So we would have 15-year period of data. This would be possible. And the question to US community is also, is it worthwhile doing that? Would there be an interest of such long-term data of global daily observations for the free troposphere? So, and then another perspective is that we can generate profiles of isotope logs in the troposphere from satellite data. And this can be done by combining different products obtained from different sensors, because different sensors have different vertical sensitivities. And actually this works like also like a data assimilation. That is, we use a first observation from satellite, which is our IASI observation as the background state, and then on this background state we put on the top a new observation, which is a total column observation that is provided by another satellite sensor, which is DROP-OMI, and thereby improve the knowledge of the atmospheric state. That is, we get improved profile information with this assimilation of the new observation. And you see here the gain matrix, or the Kalman gain of this assimilation program here for delta-D. And you see here really that we can improve the information typically in the lower troposphere. This is also what we expected. And this here is then a view on the averaging kernels. So the averaging kernels, I showed them several times already. They inform what, where does the information come from what altitude that I'm actually having my data then finally. And you see always, if we only have the IASI data, we always have a problem of sensitivity close to ground, which is typical for a thermal nadir sensor, that you're not sensitive close to ground due to the limited vertical thermal contrast close to ground. But if I add the additional data from total column measurements from DROP-OMI, so DROP-OMI does not measure profiles, it just measures column integrated water vapor isotope log ratio, it can measure it. And if I combine it with this total column data, I can really significantly improve the sensitivity close to the surface, and I can then really measure a kind of profile. So I can really distinguish isotope log ratios from ground to 2.5 kilometers above ground and the water isotope log composition above 3 kilometers.
Please conclude.
Yes. Okay, sorry. Then this is here on validation of this surface near data product. On the left, you see here the MUSICA IASI data. Without this combination with the other data, you see here some good agreement with the reference, NDAG is the reference, but you don't agree on the one-to-one line. And you come to an agreement on the one-to-one line if you combine it, but you also have increased noise, which is can also be expected because you now have 2 different measurements, and that means also noise from 2 different experiments. But if you average, let's say 20 observations, you come here to a noise level that is really acceptable of 25 per mil. So, oh, sorry, no, I would like to go to the conclusions. No, it was the other way around. Yeah, okay, so coming to the conclusions, sorry, I have to go through all it again. So my question to you maybe is, where should we put efforts now? Is it more interesting for you as community to get long short-term global observations from satellite instruments, or is it very interesting for you to have profiles observed globally on a daily frequency? So this is maybe a bit the question I would like to listen to you. Okay, thank you very much.